Excellent. Now I can see it as well. So what we're going to talk about today is small charges of natural refrigerants. And the topics are a legal overview or a framework. And then Claes is going to present two of his projects, the Pentaprop and the ProPack. And finally, I will wrap up with the EcoPack project. But to start with, I'm just going to say a few words who we are. Claes Andersson has been the driving force behind this project. He's been working a long time in the industry. He took part of the work titled to transition within Electrolux of changing refrigerants, first from R12 to R134A, and then further to R600A, that is isobutane. And the last 20 years, Claes has been working as a consultant in his own firm within this field. And he has also been working as a researcher tied to KTH energy technology. Myself, I stumbled into this field around 8 years ago while working at a startup and running a lab test at KTH of a thermal solar collector. After a few years as the secretary of the Energy Agency Research Program, EFSIS, I started at the Association for Refrigeration and Heat Pumps, where I still am today. Working with, amongst other things, our research program, Varmt och Kallt, as Morgan mentioned, that we run together with the Swedish Geoenergy Center. So to start with, I will give an overview of the frame we're working in, and then we get into the details. So here we have our Earth, and the technology used is simply astonishing and part of most people's life around the globe, from keeping food fresh to heating homes. But the refrigerants we use also impact all of us, not only locally at the plant where they are produced, or during leaks at production, at the installation, or during dismantling. No, when the refrigerant leaks, they end up in the atmosphere and spread out around the world. And as we know today, with the potential to do great harm. So I would like to highlight some wise words from the first man in space, Yuri Gagarin. When he saw the Earth from above, he said, "People, let us preserve and increase this beauty, not destroy it." And I think that could be a wise word for the lecture today. So the first international agreement we had that regulate the refrigerant, we all know, is the Montreal Protocol. And this was a realization that the refrigerant that we had used for almost 60 years damaged the ozone layer. The science behind it was that the CFCs and the HCFCs were broken down by photodecomposition. That is when the sun is shining on the molecules and they break down into pieces. And this started a chain reaction that damaged the ozone layer high up in the stratosphere. So 1987, the first protocol was signed to ban CFC and HCFCs. So here we had a choice, or the industry had a choice. Should we go back to natural refrigerants, or should we go over to a new synthetic refrigerant called HFCs or F-gases? On the top here, we can see how successful the Montreal Protocol was to stop the CFC. The increase of these in the atmosphere almost stopped immediately. But we can also see that the choice we made was to switch to HFCs. These quickly rise in the atmosphere from being non-existent because they are man-made. So before we started making them, they didn't exist in the atmosphere. And when we started using them, they of course increased quite rapidly. The next big agreement that influences us all is of course the Paris Agreement. And this is a realization that our emission, mostly carbon dioxide or other greenhouse gases, raise the mean temperature. And this led to an agreement 2015 to limit the global warming at 2 degrees and preferably 1.5 degrees. and the underlying document for this was the 4th report from IPCC. Tied to that and to the Montreal Protocol is the Kegali Amendment that came the year after the Paris Agreement. And this is when we realized and understood how strong the greenhouse gases from HFC were. Most of you know this, but I still want to highlight it, that for one of the worst, R33, 1 kilogram of this refrigerant is the same global greenhouse impact as 14,800 carbon dioxide kilograms. So they are really, really strong. And even the ones we use today and call low GWP values like R32 still, in my eyes, have really high impact. The Kegali Amendment goal was to achieve over 80% reduction of the HFCs by 2047. The EU commitment to the Paris Agreement was a 30% reduction from the levels held in 1990 of greenhouse gases. And the EU's commitment to the Kegali Amendment was the European F-gas regulation, where it states we should reach a 79% reduction compared to the levels 2015, measured in carbon dioxide equivalents. And the idea here was that when we place less refrigerant on the market, the prices will rise and the industry will by itself change to a lower GWP refrigerant. And here we can see the price rise in percent for a couple of refrigerants. And as we can see, when the first step down, 2017 was, the prices did rise really rapidly. But after that, they have actually fell. And this is due to maybe illegal import, or maybe a lot of stockpiling, or maybe that it has been a lot of speculation on this. So we don't really know, but the idea was that the price should rise in the same way as, or inverted as the step down was. So we can say, yes, it has worked, but it has been a bit too volatile than it was, the idea was. So what is to come? What we know is that IPCC has given out a new report, and that is a report on global warming of 1.5 degrees. And this one states or highlight that we really should try to keep the global warming no more than 1.5, because then the Earth will be not such a fun place to live at. We also know in the last weeks that the European Green Deal was signed, and here we have raised the targets. The target reduction for 2013 is now 55. Previously it was 30%. And we also have a long-term target that we didn't have before, and that is that 2015 we should be climate neutral. And for me, the second target there is almost more important. See the chat is something. I hope most of you can see it. At the moment, the F-gas is under revision, and at the end of the year, we will have a new proposal for it. And my guess, kind of qualified guess, is that we will have a faster phase out of the F-gases. This step down will go faster as it was compared to what it was before. We will have more bans, direct bans. And we will also try to curb the illegal import. Today, some association and so on estimate that 30% of the sold refrigerants on the market, F-gases, are illegally imported to EU. So I'm pretty sure that the new outcome of the F-gas regulation will try to handle this. So we know that F-gases will not be options long term at least, but now we have a new type of refrigerants, HFOs, to choose from. So once again, we have this choice. Are we going to choose natural refrigerant, or are we going to use the new synthetic HFOs? So I just want to say a few words about HFOs. HFOs are made up with the same atoms as HFCs, but include a double bond between two carbon atoms. This means that they are more reactive and therefore a much lower GWP. When they enter into the atmosphere, they will break in maybe a day or maybe a couple of weeks, compared to the F-gases, who could stay for years or maybe decades before they broke down. We also know that they are made up by a fluorocarbon bond, or maybe many fluorocarbon bonds. And this is one of the strongest bonds within organic chemistry, meaning that once they are released into the atmosphere or put out into nature, they will not break. They will stay there for a very long time. HFOs are part of the group of chemicals called PFAS. Normally when we talk about PFAS, it's longer chain. That means they have more carbon in them. But these are also part of the PFAS group. And just as an example, I took R1234ZE here to show what they look like. So in the angles, we have the carbon atoms, and attached to these, we have fluor atoms. And somewhere in this chain, we have a double bond, and that's where the two parallel lines is for this example. And this is then what breaks and make them make the much lower GWP value. The biggest concern so far with HFO is that they degrade into something called TFA, or 3-fluoroacetic acid. And this is true for some of them, like R1234YF, breaks down completely to TFA. On the other hand, there are other examples like R1234ZE that doesn't break down to TFA. But TFA is nothing new. Also the old F-gases, HFCs, like R1234A, also break down partially to TFA. We know that the HFOs and also the TFA is airborne, meaning that when they are released and broken down in the atmosphere, they will travel around the globe. But we also know that when it rains, they will be washed out from the atmosphere, and then they will follow the rainwater wherever it goes and stay there. And this is since it's not biodegradable. So that means that everything we put out into the atmosphere and then get washed away with the rainwater will get accumulated somewhere. We know that TFA occurs naturally, but only in the oceans. So if we find it somewhere else, like in lakes or in glaciers or something like that, then we know it's man-made. For me, who is not a chemist, all this doesn't say that much to me. Does it mean it's dangerous or not? So I've been trying to read up on this. And what I eventually found was that the drinking directive in EU has been revised and went into, order last year in the end of 2020. And what's new, amongst other things, is that there are two new limits. One is the limit for PFAS of 0.1 micrograms per liter of 20 known PFAS that we know are harmful. But there's also another new limit, and that's 0.5 micrograms for a total PFAS concentration. And if I understand this correct, that means that also the TFA, which is a PFAS, will be included in this calculation. So does this mean, is it a lot or is it not that much? Luckily, the Danes, the Ministry of Environment of Denmark, has performed a study where they have measured the TFA concentration in freshwater wells. So they looked on 247 wells, and in most of these, in 290, they did found TFA. From this, they concluded that since it's not only locally, it must have come from the rainwater somehow, that it's spread out that much across all Denmark. The limit they found was that in 97% it was 1 microgram or less of TFA in the wells, and the highest concentration is 2.4 micrograms per liter. So for me, these two look a bit scary, but we will see what happens. The next question is, what happens with HFOs plus sunlight? Is that a problem or so? We saw that R1234ZE doesn't break down to TFA and has a really low GWP value, which looks like it's really promising from an environmental standpoint. I was a bit dubious to take this because the facts are from a preprint or a preliminary version of a manuscript that has not completed peer review at the journal. So please take this with a grain of salt, but I think it still can show the potential risk of these substances. So what we have is R1234ZE that breaks down to something I won't be able to articulate, so I let you read it. This really hard thing to articulate, then when it gets hit by the sunlight, by certain wavelengths, break down to something called CF3. In the percentage of 11%, they say, plus minus 5%. So what is this CHF3? That is actually this R23 that we had before, which is one of the most potent greenhouse gases of the HFCs, with a GWP of 14,800. So this will then lead to that R1234ZE that has a really low GWP value. All of a sudden, after it has been decomposed in the atmosphere, end up with a lot higher GWP value. So once again, it's a preprint, but it kind of shows the danger with this. Could this then be true? We have the HFC observation in the atmosphere. Here we look on the top on the total amount from 1990 up to 2018. And what we know is that when HCFC22 is produced, HFC23 is a byproduct. And in the past, this was vented without doing anything to catch it. But up till 2016, all refrigerant producers had then reported that they have abatement in place, meaning that the byproduct should be taken care of, collected, and then destroyed. So according to the reporting up to 2014, the growth rate was really close to the produced amount of HCFC22. But for some reason, after 2016, this didn't match any longer. And it could be then that the HFOs, R1234ZE, could have an impact and produce this HFC23. And that's why it all of a sudden the growth rate is rising again when it actually was supposed to be 0 here. It could of course also be that producers still are venting the HFC 23, but it's one explanation. So the choice of refrigerants for the future, for me personally, I think it's pretty clear that too many uncertainties with synthetic refrigerants containing carbon and fluor. The long-term effects are hard or impossible to prove before the actual harm is there. We saw with the CFC that it took 60 years before we understood that there is a problem with them and could regulate them. The next thing is that legislation work is a lot slower than finding new substances. We've gone from the HFCs and then we added a double bond on this, and all of a sudden we are outside the scope of the F-gas regulation. With this said, the REACH directive is currently undergoing a revision, and the REACH directive in EU is a directive that ban different substances or regulate how they should be used. And there is a discussion at the moment to ban the whole PFAS group. There will be a lot of discussion about a lot of lobbying in different direction here, so we will see what happens with this. But at least for us, we're back to where we started, 1834 in natural refrigerants. And for our application that we will show today, this means propane and isobutane. I will now give the floor to Claes. No, sorry, I still have a few slides. Okay, the challenge we now have to deal with is the flammability. Both propane and isobutane is highly flammable, A3 class, the highest flammability class of all refrigerants. The easy way to deal with this is to follow the harmonized standards. And what does harmonize mean? It means that if we are using a standard following that, that also means that we are following all laws connected to this field. And for us, this is then the EN 378 and EN 6033355-2-40, which is a product standard for air conditioning and so on. And in both of these standards, the lower limit is 150 grams, meaning that if we are below this limit, we don't have any restriction of room sizes, or we don't have to take any extra precautions. So that has been the starting point for all these projects that keep the refrigerant charge below 150 grams. If we look into the future of these standards, a lot of work has been done to better understand the risk of A3 refrigerant, and a lot of risk assessment has been done. For instance, a great study has been done on leak hole and the size of these. One have taken 1,000 actual damaged item and measured the leak hole. And it was found that 95% of these had an area of 0.5 square millimeters or less. Another big topic has been dilution, and here it has been found that it's really important of what height the release is done, meaning that if the release is done at floor level, we will sooner reach an explosive or a flammable atmosphere than if the release is higher up in the room, meaning that the height of the release will be an important factor. From one of these papers, I just took the mass flux. From knowing the leak hole size and knowing the pressure, we quite easily can calculate the mass flux that will be from these leaks. And here it has been used two different temperature, 25 and 45 degrees. And what we can see that for R32, for example, that has quite high pressures, the mass flux is all the way to the right, around 150 for the 45 degree. And all the way to the left in the graph, we have the R600 and R600A. And since it has so low pressure, it also means that the mass flux from this will be a lot lower. And this will also influence how much refrigerant charge we can put in a room that will be allowed. In the middle, we have propane, and there the conclusion was that the mass flux will be 30 grams per minute, and at the higher temperature, it will be 65 grams per minute. And the mass flux that has been used in the standards today are a lot higher, meaning that we will see an increase of allowed charge in the future. Some standards also have linked the total charge of the system to the mass flux, and this has also been proven that it's not likely. It's more likely that it's the size of the leak hole and the refrigerant that sets the mass flux and not the charge, the total charge. So an example what it will probably look like, I borrowed this picture from Asbjørn Vonsild, and this is then the revised edition of 60335-2-40 that hopefully will be released late this year. So the blue field, we have our 150 grams, they will stay. On top of this, we have the red standard system that is then dependent on the room area. Then we have introduced a new definition called enhanced tightment. I will not go into details here, but there are a lot of different things we need to do to classify a system as enhanced tight. And finally, we have a circulation airflow. If we can make sure that the air is circulating, then we have a higher dilution. So we can see that we quite soon, a room with 20 square meters will then be allowed with 1 kilogram. And a really big difference compared to the standards today is also that this will be calculated on the releasable charge, meaning not the total charge. So if we use safety shutoff valves in the refrigerant pipe, then we can calculate the allowed charge on what will be released and not the total. The same thinking and the same background will be used for EN378. So these will also be updated soon. So with this said, now I will hand over to Claes.
Okay, thank you, Victor. Okay, could you see my screen?
Yes, it works. We see it.
Thank you. Okay, first of all, I want to thank SKVP for giving me the opportunity to participate in this seminar. And I now will show some examples of possible techniques to really use low amounts of flammable refrigerants. I call it natural refrigerant opportunities. I will tell you about an old project. Some of you probably have heard about this before at previous presentations. It's about a ground source heat pump, was finished 2018. And I'm now running another project aiming for doing the same for a split air conditioner. And finally, Victor will talk about a high temperature heat pump, which is also a running project using more or less the same basic principles. Starting then with the so-called Pentaprop project, which was a project aiming for a small family home ground source heat pump. And the reference system for a very small capacity heat pump is a 5 kilowatt standard unit with about 1 kilogram of 407C with quite some carbon dioxide footprint. It also normally uses brine additives in the coolant. So the Pentaprop project target was to do exactly the same, but with less than 150 grams, this magic, a little bit strange, safe limit for propane. And the project also used pure water as coolant. I shouldn't talk about that today. That's another topic. Okay, so this is be a little bit about the technology used. And since this project was finished, there's been an increased sort of ambition, at least within Europe and also in the US, to extend the use of ground source heat pumps. So I know that there's a lot of investments going on within the industry to meet these demands. All these projects is about the team. You have to set up a good team. So in the Pentaprop project, we have AREC, which utilize the development of new plate heat exchangers. We have Professor Emeritus Erik Granryd, who is an important person in all these projects, and some then manufacture of compressors for vehicles. Nibe system manufacturer, Sanhua, a big manufacturer of refrigeration components and heat exchangers. The project had very good and important support from the Swedish the Applied Thermodynamics and Refrigeration department at KTH. Actually, this department and Professor Björn Palm made this possible by very early studies many years ago in minimum charge system. Linde supporting with refrigerants, and I was the manager and performer, and it was founded by the Swedish Energy Agency. And I have to point out, especially Professor Emeritus Erik Granryd, without him, nothing of this we will tell about today could have happened. He's an excellent supporting force in all this work. So shortly about the system. This is a standard refrigeration system, but with an important extra, not normally used internal heat exchanger, which give off heat from the hot liquid to the cooled suction gas over this unit. And initially we have no filter dryer and no receiver, which is, I would say, dangerous from a quality point of view, but very convenient if you want to minimize the charge. In other aspect, it's a standard system with plate heat exchangers exchanging heat between the condenser and radiator water, and in the evaporator to the coolant going down in the collector borehole. So this is what these units look like, and it's the illustration of minimum internal volumes and minimum corresponding charge. So this is the inclined condenser, and you have the pressure line here as short as possible, and then the outlet from the condenser on the refrigerant side is behind the compressor here and let in to the liquid side of the internal heat exchanger, and the liquid side is these flat pressed copper tubes you could see on top here. And then the liquid is let into the expansion valve and into the bottom of the evaporator, and this is the suction line going back to the vapor side of the internal heat exchanger. And via the internal heat exchanger behind the compressor here, you could see the suction line coming up and into the compressor. And you could see that the overall sizes of the unit is quite compact. So I should tell you a little bit about the components in the system and what makes the difference and what is important in terms of charge. This is just an example of a representative compressor for a standard similar unit. So this is a scroll with about 1 liter of oil weighing about 20 kilos, and that would capture for this application about 70 grams of propane. So this one is replaced then by this Sanden vehicle compressor containing less than 1 deciliter of oil, very small, low weight, and this takes about 15 or less grams of propane. Huge difference if you're hunting down the charge. And the reason of this is, of course, the very small internal volumes on the discharge and suction side, respectively. And it's worth noting that the inverter control of this variable speed compressor is built in. It also has some powerful logic and communication facilities for electronic communication. This is made for climatization of both batteries and compartments in electric vehicles. It's a scroll pumping wheel, and the motor is for 300 volt DC. That was, at least in the beginning, common standard voltage in electric vehicles. It has ball bearings, which both is a plus and minus. The plus is that this is not very sensitive for the oil for the lubrication, so it's really hard to damage this compressor by having lack of oil. It's a huge speed range. I haven't seen anything yet like this on the stationary market, ranging from 800 to 8,500 RPM, and this is of course quite an opportunity to achieve a good capacity range with corresponding good seasonal efficiencies. The size of the scroll wheel is 33 cubic centimeter per turn or revolution. This compressor is made for vehicles. It means it's very tough. It could withstand tough vibrations, very hot climates, very high discharge temperature. It's really made to survive rough conditions. So this is on the plus side. On the minus side, this is made for HFC refrigerants. So that is a problem when talking about compatibility with lubrication oils. Also, the lifespan for vehicles is much shorter than for stationary applications. This is a problem. And finally, this one is semi-hermetic. There are bolted joints here and here. And also the connection is not solderable. It's O-ring joints. But the good thing is, since this project was finished and we have continued the cooperation with Sanden in other projects and in other industrial aspects, Sanden has invested. So now they have tested and proved sufficient oil combinations and lifespan with propane. So now it's only a matter of investment. So Sanden says they could provide an hermetic compressor with solderable connections on request within a couple of years. It's just a matter of investments, not technique or limitations in what is possible. The heat exchangers. This is like a chicken race between good heat transfer and refrigerant charge, and low charge with small volumes could induce pressure drops. So normally the standard type of plates in plate heat exchanger is this fishbone pattern. A plate heat exchanger is put together by numerous of these plates soldered together with refrigerant on one side and water on the next, and so on. And the standard technology has a distance in between plates of about 2 millimeters. That means that you capture about 0.9 liter of propane per square meter. Sorry, the internal volume is 0.9 liter per square meter heat exchanger area. And for this Pentaprop application, that would correspond to approximately 70 gram and 120 gram of charge for the evaporator and condenser respectively. And you could see, to reach 150 gram, you already lost the race from the beginning. So I just want to refer to very old work made by Professor Björn Palm and his team at KTH. This is a very interesting, funny heat exchanger made many years ago with quite small internal volumes. But 2013, Danfoss introduced this microplate heat exchanger with only 1 millimeter distance with the plates. And this one is a quite interesting technique, even though the ports are a little bit too big to be optimized for minimum charge. I think nowadays they could provide plates with smaller holes, especially at the outlet from the condenser where you have liquid. But in the Pentaprop project, together with Eric and Professor Emeritus Erik Granryd, we developed new plates and put together new heat exchanger where the distance in between the plates on the refrigerant side was less than 1 millimeter. It was measured in tenth of millimeters with quite low charge per heat exchanging area. And we had about 25 and 50 gram of charge in the evaporator and condenser respectively, and that is more than half standard technology used. And unfortunately, still today, I think common practice is this, what I a little bit, well, unpolite called old-fashioned technology, even though this actually is available. I'll come back to that in next slide. In a few, next after this. This is just showing the work behind this. Eric and Erik, we made different plates with different press patterns, with different depth, providing different distances between the plates. So this narrow, this is the refrigerant channels, and the larger spaces here is for the water. So you could see that this heat exchanger is heavily unsymmetric, which is beneficial for maximum performance. And we tested with lower and lower distances until you could see the solder clogging the channels. So we found the limit for what was possible with standard technique. And then we took some margin beyond that, saying that compared to the Pentaprop heat exchanger, you could go further with more studies on this technique. You could do even more or less voluminous heat exchangers. So this is just a little example of how the pattern could look like. It's a combination of different dots and dimples and press patterns. And this is a very interesting academic work from Professor Erik Granryd in how to do the best trade-off between heat transfer, charge, and pressure drop. And one thing I would like to point out, this is the pattern at the outlet of the condenser. Everywhere where you have liquid, you have high density, so every cubic centimeter of internal volume takes up many grams of charge. We don't like that. So here is the end of the condenser where you are supposed to have liquid. So here the liquid comes and turns around the inlet of the coolest water, the inlet from the water, which is the coolest point of the whole heat exchanger. So you get a lot of subcooling for a very little charge. This takes up very small volume and you still got very good subcooling. And the outlet port is very narrow, or it's optimized to give a good combination of charge and pressure drop. And the benefit of subcooling, it's important to have subcooling, even though it costs you some charge, because you increase the capacity and also the efficiency. And the good thing is actually saying that this was like a prototype not available on the market, but since the project got finished, Eric and the technology developed by Eric and Granryd was bought by Alfa Laval, and Alfa Laval actually introduced the CB24 just a few months ago, and they won a bronze medal on the natural refrigerant trade fair the other month. So this one is now available. I don't say that there is any similarities between the technique in the Pentaprop or Alfa Laval heat exchanger. I don't know how the Alfa Laval heat exchanger look inside. I just want to point out that this is a really minimum charge heat exchanger that is now available on the market. So you out there, you could start develop your minimum charge natural refrigerant heat pumps now, if you like. Okay, One very important system if you develop a minimum charge system is actually the plumbing, or how you orientate everything, because the layout, how you put things in relation to each other, determines the length of each and every one of the tubes. So you see here, you really have to minimize the length in order to get low volumes. So this is actually a little bit more difficult than what you think of in the first place, how to arrange the layout. And from that, the diameter of the tubes and the length of the tube is a trade-off of charge, of course, but you can't accept too much pressure drops. You have to optimize each and every one of the section here in order to don't have too much pressure drop, which will cost you evaporating pressure, which is a loss, or discharge pressure in this. All the gas lines has to be thoroughly optimized as a trade-off between charge and pressure drop. And of course, the liquids part is very critical. Since liquid has very high density, the charge in terms of the cost in terms of charge is very high for every cubic centimeter. So these should be very narrow as you can make them. And in the Pentaprop project, all the connection lines captured about 4 grams of propane. The internal heat exchanger, just shortly about that. The standard internal heat exchangers available on the market is normally, most often, a coaxial type. Here is an example, which exchange heat from the hot liquid after the condenser and heats up the suction gas on its way to the compressor. This one captures a lot of charge and has very poor heat transfer. So this is not an alternative. So in this project, we made an own version of a heat exchanger made up by pressed copper tube, as you saw in the picture before, soldered together with the unit. And this captured altogether about a little bit more than 5 grams with acceptable but not optimal pressure drop. There's a lot to be say why you should have an internal heat exchanger. I won't go through all of this. I could just say that I expect system to have internal heat exchanger in a much more common way in the future, and therefore we have another part of I will tell you later, we will try to develop a more commercialized available internal heat exchanger, which has the good combination of heat transfer and minimum charge, because especially for natural refrigerants, there is a benefit in terms of system efficiency. The gain for the heat given off here, which increases the heat you can evaporate, is a win. But then you increase the temperature of the gas, and that increases the compressor work. But the net effect for both propane and isobutane is a win. And there are other benefits. You could flood the evaporator without risking liquid at the inlet of the compressor. And you could also make a better control system, which is not so sensitive, since droplets remaining here will be evaporated in this heat exchanger. It gives you a more robust system, and it gives you a more efficient system, even though at the cost of some refrigerant. The expansion valve in this project was a standard thermostatic, but since the capacity range of the compressor was so huge, you have an increased range by a manual valve here. But you could see that it's very narrow, and also the expansion valve here is filled with inserted tubes in order to really minimize the charge. It was like 2 grams in this part of the system. So altogether, summing up all the components when they were put together in a system, it was about 100 grams of propane in this system at the target capacity. And the result then, how did the system work? This is a short summary of some of the performance. So on the x-axis, you have the water temperature delivered by the heat pump to the radiators. And on the y-axis, you have the heating capacity. And the lines represent different speeds of the compressor, ranging from 1,000 to almost 6,000 RPM. And you could see that we could reach not only 5 kilowatt, but easily 10 kilowatts with this system. Wrong direction. keeping in mind that the maximum speed of the compressor is 8,500, you could see that we could go much higher in capacity if we like, but the system was not designed, the heat exchanger was not large enough for these high capacities. But again, it indicates the potential to have a good seasonal performance with a wide capacity range for this type of compressor. One little detail that I would like to point out is, despite what everybody thinks sometimes, is that when you increase the capacity, increase the compressor speed for a given system, what happens is, in this type of system where you have no receiver, if the superheat and the subcooling is connected, you can't move away refrigerant in the receiver. So if you look at this, you have the same superheat but different capacities. If you increase the capacity by increasing the compressor speed, you will suck down the pressure on the suction side in the evaporator. And if you do that, you will lower the density of the gas, and all the volumes on the suction side will then capture less refrigerant. That refrigerant will be found as liquid on the high pressure side in the condenser. So therefore, if you compare, if you run exactly the same system with the same 100 grams with 4 Kelvin superheat, we had about 3 Kelvin subcooling. When we increase the speed and the capacity, the subcooling for the same superheat is about 10 Kelvin. So actually at the higher capacity we have excess of charge, and actually the optimum charge will be less than 100 gram in this position. So this is also it's both a problem and an opportunity in the system design and the control. There's a lot I could talk hours about this, but it's an interesting fact among many others. The bad thing, though, that the efficiency was not good enough compared to benchmark with NIBE. It wasn't good enough. So we had to do something about this, and also it's not acceptable to don't have a filter dryer. So after the project was finished in terms of a research project, we did some further studies. So we exchanged what is normally used, a quite large filter dryer, which sometimes also is both a receiver and filter dryer, to a household type of filter dryer. The molecule sieves doing the drying work is normally, though, only filled up to some section here, and the rest is void, and we don't like voids filled with liquid. So therefore we made a simple rebuild of this, taking away the voids. So it is only volumes with molecular drying sieves here making work as drying the refrigerant. And also we tested with a larger evaporator, because that was the limit for the higher capacities and the corresponding low efficiency. So going from 30 to 50 plates in the evaporator combined with this filter dryer increased the charge from about 100 to 120 grams. And then we have a acceptable, I shouldn't say good system, but acceptable system in terms of efficiency. So this was a short overview over a possibility to use natural flammable refrigerants in a ground source heat pump. Next up is the Prupac project. This is about a split room air conditioner. Now I see I'm running out of time, so I will just give you the background that there are hundreds of millions units produced per year, and expected to increase, and I think it's 1 billion hanging on the walls around the world. And one common size of this, fraction of this, is this size, a split unit with about 3.5 kilowatts cooling capacity. And today they are produced with R22. With the normal is 410A, which has quite a large CO2 footprint. And the last few years there has been a transfer to R32, which still won't meet the Kegali commitment, so this is not a final solution. Moreover, it's mildly flammable and has very high discharge temperatures. So Daikin has been the driver of this. They have a lot of patents to take care of the problems with these refrigerants. In other aspects, R32 is an excellent and efficient refrigerant. More interesting is that in Asia, during the last years, there's been a lot of units produced with propane, but it's with old technology. So they just filled standard units more or less with propane. So the corresponding unit has more than 350 gram or 350 gram or more. And that requires large room and a lot of actions, as Victor told you, in relation to the standards. You won't see them in Europe, so they are sort of dangerous. We perhaps don't want to do another mistake with new synthetic refrigerants. We don't know yet if this is a dead end. So therefore, this project was started trying to reach the required capacity with acceptable efficiency with less than 150 gram of propane. Again, the team is everything. So this time Electrolux represents the company that sells such units globally. Gränges supporting with aluminium knowledge, since they provide the material that Sanhua makes the heat exchanger of, because here we're using Sanhua aluminium heat exchanger. The same compressor, Eric Granryd, of course, and KTH supporting with academic insights, and EBM PUPs provide top skills to combine the heat exchanger with efficient fans. And it's founded by the Swedish Energy Agency. Linde provides refrigerants. And since all these units now is controlled by electronic communication buses, it's M-bus, Modbus, Linbus, and I don't manage to run the fans actually. So I have a computer expert providing the interfaces between everything. Okay, more or less the same system now with the filter dryer from the beginning and fans instead of liquid pumps. And we use what is called micro channel heat exchangers made of aluminium. So we use initially a 0.5 meter in square condenser, and EBM PUPs provided oversized fans in order to be able to test the system without limitation in airflow conditions. And we used a similar standard condenser as Evaporator, which has some drawbacks. And also the Evaporator fan was an oversized fan in order to be not limited by the fan in the tests. We didn't really know what we will end up on in terms of pressure drops in these systems. Here you could see we use the same small type of filter dryer, but this time it's a Sanhua electronic expansion valve. And this is a developed version of the Sanden vehicle DC compressor. And we use the same principle of internal heat exchanger as in the previous project. So within this red frame is everything that's in the outdoor unit hanging on the walls over the world. And this is then the indoor unit. So shortly about the components, but with less details. This is the standard type, a rotary compressor that has a huge liquid separator. Since this is very sensitive for liquid inlet to the compressor, this takes a lot of charge. Also, normally the dome here is on the high pressure side, taking a lot of charge. So this is of course replaced by the state-of-the-art compressor for the future with natural refrigerants. This scroll unit, I hope to see this one in a hermetic version soon. Though we have to add on the minus side the cost, because in this type of application, the cost of such a compressor is extremely low. So compared to the standard, this is a little bit expensive at the moment, at least. The standard condenser is copper tube with aluminium fins, huge internal volume, totally unusable for a minimum charge system. This is replaced by aluminium microchannel heat exchanger from Sanhua. So just looking into what this is what type of heat exchanger is this? Here is a stop in this inlet header. So the refrigerant is let in here and has to pass on this side and then over here through this header back to the outlet, which is down here. And if we look inside, this is just a capture from the upper left corner. You could see that this is the header, the flat tubes and the fins. So there in this heat exchanger, 0.5 meter in square, a little bit more, we have 52 flat tubes and there are 16 channels, very narrow in each and every one of these tubes. And the fin distance is about 1 millimeter and the diameter of this header, keeping contact in between the different tubes, is about 20 millimeters. An estimate says that for this system with propane, and the channels is about 0.2 liter and the headers is about 2.2 liters. We will have about 50 grams in the channels and 38 in the headers. You could see the headers is a little bit of a problem in terms of minimum charge. A little detail here is that we made a special arrangement here in order to avoid a high liquid column adding charge at the outlet. So we really keep the level of liquid and the charge at the minimum here. The evaporator, this is the standard type. This was replaced with a similar type of condenser. So here we have the inlet and it turns over here and goes out here. This is not optimal. The problem now is that this type of heat exchanger is not very well developed as evaporators. They have been used similar types in car ACs for many years, but they have huge headers with huge internal volumes. Still problems with the distribution in between all these channels. It's not a good solution, but it was a compromise. And this is how it looks like in real life in the test rig. Also, the channels is a little bit too narrow to be evaporator when a condenser is used as evaporator in this way. And also the outlet diameter is too narrow, inducing pressure drop. And as I said, it's difficult for an evaporator to get even distribution among these 52 times 16 channels. An estimate of the charge is 12 plus 36 grams. Again, the headers is a problem in terms of minimum charge. So this is just an example of the work that you have to consider each and every little part of the system that you put together in terms of pressure drop and charge for the length and diameter you use. I just take a little example here. This is the line connecting the indoor unit with the outdoor unit. So the outlet from the expansion valve, where you have two phase, to the inlet to the evaporator. Here you could see if I use 1/4 inch tube here and the line is only 3.5 meter, which is quite short for a split unit, you will have about 4.4 grams of charge. But this comes with a huge pressure drop. So this is an important little detail. You have to really consider this line in order to have a minimum charge. You have huge pressure drop, but then this is a serious coupled expansion valve. So this have influences of the control and selection of the expansion valve. You have to make a good judgment here so you don't lose the control range of the expansion valve. So this is the charge distribution estimated, not measured. So before the project, and it turned out to be quite accurate actually, you could see that most of the charge is in the condenser and then in the evaporator. And I want to point out that the compressor is a really utilizer for these techniques. It's very little charge to be in the compressor. And of course, all the other components is kept at absolute minimum in terms of charge. So this is a picture of the test setup. Electrolux also provide very exclusive test facilities. They have a beautiful laboratory in Stockholm. So here is the evaporator connected to their measurement device, measuring the humidity content and the temperature of the air and the airflow. and here is on the inlet side. So the difference of the humidity and temperature before and after and the airflow determines the capacity very accurately. It's very difficult to measure this accurately. Here you could see some pressure meters, and here is the connection hoses to the indoor unit in the other test room. Same type of measurement. It's a fork sucking in air, which is measured in a special device here. So you could measure the capacities. Here you could see the compressor and the fan, and this is the condenser. So what did we achieve? So the very first results with this is an ongoing project. So you have the compressor speed on the x-axis, and you have the cooling capacity on the y-axis. And you could see that we met the target 3,500 watts at about 2,000 RPM. So the capacity is already okay for the target. And actually, you could see, referring to the maximum speed of 8,500, I would say isobutane would be an interesting alternative, because then you have lower pressures and you have a little bit higher efficiencies. And you could use that, since the capacity, we have actually excess of capacity in this unit. On the other hand, the efficiency was not, again, good enough. So you could see that the efficiency here at the target capacity at 2000 RPM, the efficiency was about 3.3, and the benchmark from Electrolux required 3.5 to be a good unit compared to today's other units. So we conclude so far in the project that with 150 gram, which happened to be a very good charge for the first prototype, we could reach 3.5 kilowatts at 2000 RPM, 12 cubic meter per minute evaporator airflow, and this 30 condenser airflow. And this is not because this is the optimum airflows. This is airflows more related to acceptable noise levels, but the efficiency was not accepted. So the next step in the project is solving these problems by improvements. And one of the problems turned out to be, I will be very quick now, but it illustrates, I apologize for the poor quality here, but I have divided the evaporator in different sections here. But at the outlet upper right corner here, this is this upper right colored corner. You could see the white red area here is where you have superheated vapor. This means bad distribution as expected. This has to be improved. Also, the internal heat exchanger showed to have a little issues with pressure drop. So we have initiated a cooperation with Gränges. So we're actually now building a totally new type of channel and aluminium type internal heat exchanger designed by Erik Granrid, which is in a cooperation with Gränges. So we're actually manufacturing this at the moment. So we're excited to see how it will turn out. It will have low charge, high heat transfer performance, and low pressure drop. And Sanhua has actually developed and extended the development of a special evaporator. So instead of using the condenser as evaporator, we will now, and it's actually stuck in the container passing the Suez, so it's a little bit delayed, but this is specified for the project by Sanhua. It's a little bit smaller, and that will make it more convenient as an indoor unit. It's instead of half a meter in square, it's like 0.4 meter in square. So here we have only one pass from the inlet through all the tubes and out. That will give lower pressure drop. And this has an O-ring arrangement with a distributor arrangement. So Sanhua has tested and developed a new type of distributor for this evaporator. So hopefully we will have even distribution. And that will hopefully improve the performance and reduce the charge of the evaporator, and also then improve the efficiency. EBM PUPs providing new fans that will fit and look more like a real application. So there is new fans for the condenser on the right here, which will fit. We will use the same condenser in next step. And Sanhua and EBM PUPs, we have also a new evaporator fan that is optimized for the calculated expected pressure drop for this new evaporator. So this will be the indoor unit and this will be the outdoor unit in terms of fan heat exchanger arrangement. The architecture for this will look something like that hanging on the wall. It should be mentioned that this heat exchanger can be curved, bended, so you could actually make the evaporator indoor unit look like they do today. But we don't do that within the project. We don't have time and resources to do that. But the condenser architecture, this is a standard unit with old-fashioned heat exchanger with a rotary compressor, exactly the same capacity. And this new technology will fit in very smoothly in the same architecture. Another issue I want to stress is the charge.
Claes, I'm very sorry for interrupting you because this is very interesting. I just want to let you know that we're already 50 minutes past the end of the seminar. So if there's any possibility to wrap it up, it would be.
I wrap it up. Okay, there's an issue with liquid in the headers, so we have initiated to avoid this liquid standing still in between the tubes. We have made with the new type of headers that the tubes doesn't stick in and make liquid pools available. We hope to be able to test this in order to further minimize the charge, and Gränges tells us that they could use header like this in the future, which we now will test the influence if it's worthwhile doing this. So this will be a new technology with the tubes sticking in less and that liquid really enters the tubes without forming pools. But we also have to reduce the pressure drop, which was too high in the connection lines between the indoor and outdoor unit. And we will increase the length from 3 meters to 6 meters at both lines. And that will increase the charge with about 9 grams. So hopefully the combination of the new smaller evaporator, but this longer and larger connection lines will keep us below the 150 gram levels. I could just shortly say that if you want a combined heat pump and air conditioner as we use in Sweden, that will add some extra 8 grams and bring in some complicated issues in the heat exchangers in order to get them work properly, both as evaporator and condenser. Thanks for listening.
Thanks so much, Claes, and thanks, Victor. This was very interesting, and I'm very sorry, everybody, that we went a bit past the 10 o'clock. But thanks a lot, and I think it's we should have some time for some questions now. And you can either ask your questions in the chat or just raise your hand and I will give you the word.
One thing, Morgan, we still have one part about the EcoPack. Should I run it or should we save it to later?
I really think we need to save it because we are already 17 minutes past. It's very unfortunate, and I really hope we should have had more time for it. Maybe we can see if we can make another webinar on the topic. But let's have some time for questions. I think we had a question in the chat, perhaps. Let's see. We have a question from Jonathan Vlastuin. The 150 gram limit is for indoor units. So what is the limitation for AC units?
If you consider a split unit, you could expect all the charge to be released at the indoor unit since they're connected, and you can't separate the charge in between the indoor and outdoor unit. You have to, I think, imagine the opportunity that everything is released on the inside as long as they are connected. So it's the same 150 gram.
I can add to that. In the updated version, if you add shut-off valves between the outdoor and indoor and have a sensor that shut these valves, then you can actually separate the indoor and outdoor. But today it's like Claes says, it's the total filling charge.
I could add, I think the air conditioning industry is extremely cost sensitive. You can't add anything. So hopefully if we could get down the price of the compressor, the microchannel heat exchanger is actually less expensive. And my experience at Electrolux, everything getting smaller, getting cheaper with large volumes. You can't add things. I think this internal heat exchanger also would be questioned by the industry at the end of the day.
Thank you. We have another question here from Patrik Sjöstrand. Does it matter if you put a release valve in the outdoor unit?
I would say no. The release valve is only for external fire or something, not a normal operation. So no.
Thanks. And there's a question here from Einar Gudbrandsen. Will we have to stay below the 150 gram limit when products are according to the newest version of EN 6355-2-40 enhanced tightness?
That was this graph that I showed, that there are a lot of parameters, but we could quite easily go above 150 grams. But it depends on a lot of parameters.
I would guess that the minimum charge that is considered safe, that will require no extra precautions, would be increased. I think so. According to the studies by this Daniel Colburn, it's likely that you could do that safe, let's say to 200 grams, but I don't know if and when it will happen.
Okay, thanks. I can't see any more questions, and so I simply suggest that we end this breakfast webinar. Thanks so much, Victor Helén and Claes Andersson, for your presentation today. And to everybody, have a wonderful day.